Thanks for your interest in our paper. My name is René. I am a PhD student at the German Research Center for Artificial Intelligence, and within our cooperation with BMW, we have developed a method that can extend any scene flow estimator to use multiple frames and by that to improve the accuracy. In computer vision, scene flow is the problem to find the 3D position and three-dimensional motion for every visible point of the scene. And classically, stereo cameras are used to solve this problem. And if these cameras are calibrated and rectified, scene flow becomes a dense matching problem across multiple images. At least 4 2 time steps from a stereo camera. Now, why is dense matching still a difficult problem? We have very strong representations for image points and extreme computational power and efficient matching algorithms which can solve this quite efficiently and well. However, the biggest challenge that remains are occluded areas, because you just cannot match what is not visible. And to illustrate this, we have here some examples from the Sintel movie, where you can see the 2 stereo frame pairs, and in the bottom row, highlighted in red, areas which are occluded in at least one of these views. And it is impossible to find the correct scene flow for these areas by matching alone. Therefore, in previous work, some kind of regularization was applied in the form of a smoothness assumption, or by filtering and interpolation, or by exploiting context knowledge of the surrounding areas. However, we argue that it is better to avoid the problem of occlusions by using multiple image frames. When adding only one additional frame pair, as seen on the right here, only very little areas remain which are occluded in all of the views. So it's possible to find matches across multiple frame pairs which are not occluded everywhere. However, the issue that arises then is how to relate the motion between these multiple time steps. Often a constant motion model is assumed. However, in our work instead, we want to learn the relation of motion from data. And how is this done? Our framework uses exactly these 6 images, left and right view, at 3 time steps. And then, at first, any off-the-shelf scene flow estimator can be used to estimate the forward and backward scene flow with respect to the same reference frame, which is highlighted with a red frame here. Then a dedicated module inverts the backward scene flow into forward direction by applying the learned model of motion. And at this point we have 2 forward predictions which happen to have very little overlap in their respective occluded areas, as just illustrated on the previous slide. In a last step, we merge both these forward predictions by a fusion module which predicts weights between 0 and 1 to apply a linear combination of the 2 forward scene flows. This way we obtain a refined fused multiframe result, and as a byproduct the soft occlusion mask, which is defined by the weights of the merging module. In our paper we have evaluated all the intermediate steps of the pipeline and also submitted results to the official Kitty benchmark. What we are showing here is the improvement of our multiframe extension over a variety of scene flow estimators. These include mostly deep neural networks, but also classical approaches. What is reported in these diagrams is the outlier rate according to Kitty, which means lower is better. And the results of our extension are given in blue. The dual frame baseline is shown in red on top of that. It is evident that the extension achieves an improvement in almost all cases, and a significant one in many of them, especially for the occluded areas shown on the right side. For more results and an in-depth analysis of our approach, we would like to refer you to our paper. If you have immediate questions and for discussion, please join the question and answer session or drop me a mail. Thank you and have a nice day.